Nuclear reactions can be thought of as a type of emission process where the nucleus emits a particle, or a capture process where the nucleus captures a particle. And we're going to take a look at some examples. We'll start with something called alpha capture. The Greek symbol is this, and so that's commonly used as a substitute for writing out the word alpha. And for alpha capture, we can take the beryllium atomic weight 8, react it with an alpha particle here, which is the equivalent of a helium nucleus, and we would create carbon-12. This kind of reaction occurs inside of stars, where a beryllium atom would capture a helium atom, or the helium and beryllium would rather fuse together and give us carbon-12, and then quite a bit of energy is released. Then there is a process called proton capture. So we can have a hydrogen atom and another kind of hydrogen atom, in this case one that has a neutron. So this can also be written with a D instead of an H. It would be deuterium. And if this deuterium or hydrogen here captures this fellow here, that's just simply a bare proton, then we could create the element helium-3. So the isotope of helium with an atomic weight of 3. There's also quite a bit of energy released in that process, and both these things happen inside of stars. There is also something called neutron capture. So neutron capture would look like this. We could have nitrogen-14 that has an atomic number of 7. It can capture a neutron with an atomic weight of 1. It has no atomic number because it's not a proton. And that would turn into carbon-14 with an atomic weight of 6. And this can release a proton in the process. As this reaction occurs in nature, this is how carbon-14, which has a relatively short half-life, is replenished in Earth's atmosphere. So carbon-14 has a half-life of about 5,700 years or so. So in a few tens of thousands of years, carbon-14 would be gone. Well, it would be, except for the fact that we have cosmic rays, which yield neutrons, and nitrogen, which is abundant in the atmosphere as nitrogen and gas, can absorb some of those neutrons to create new amounts of carbon-14. And then we have beta capture to move on to our other forms of reactions. So with beta capture in geology, we have the very important potassium-40, which can capture a beta particle and turn into argon-40. This is a type of decay, although it's really not, it's classified under a type of radioactive decay dating method, but it's really kind of a special kind of decay where we're actually building something rather than having something split apart. The potassium-40 nucleus is absorbing a beta particle to give us a new kind of element, argon. So the beta particle, this is a negatively charged particle. Potassium has an atomic number of 19. So the beta particle will react with a proton inside of the nucleus to give us a neutron with no charge. A proton is used up in this reaction, so we get argon, so we've got one less value for the number Z for the atomic number, but notice that the atomic weight stays the same because protons and neutrons have the same atomic weight. So that's a process that's called beta capture, B-E-T-A, or we can use the symbol beta. Then there is beta emission. So with beta emission, we have this kind of example. We can take rubidium-87 with an atomic number of 37, and it can decay into strontium-87 with an atomic number 38, plus the emission of a beta particle. What is this beta particle? It's an electron from the nucleus. In this case, a neutron has decayed into a proton plus an electron. So since a neutron is decaying into a proton, we don't change the atomic mass. It stays at 87. but we've increased the number of protons, so a neutron here turned into a proton. That increases the number by 1, and in doing so, this fellow leaves the system. That's the beta particle that is being emitted from the nucleus. Then we have positron emission, and positron emission, we can have phosphorus 30, atomic number 15, can decay into silicon 30, and that has an atomic number of 14. Notice this is the opposite here. For the case of beta emission, the atomic number went up. Here the atomic number is going down. And so we are releasing a beta particle that has a positive charge. So this is something that you're probably not, perhaps not familiar with unless you've studied particle physics. It's something with the mass of an electron, but a positive charge instead of a negative charge. And so you can think of a proton as having is being equal to a neutron plus a positron. So if you think of a proton as being equal to a neutron plus a positron, if we have a beta particle that's being emitted, then you can consider this as kind of a decay process where the proton turns into these two fellows here. Since a proton is turning into a neutron, the mass doesn't change, but we're losing a proton because it's turning into a neutron, so the atomic number goes down from 15 to 14, and that beta particle that is positive, this positron that gives the proton its positive charge, that's what's being emitted, so that's leaving the nucleus. And then finally, we'll have something that we'll call alpha emission, and we'll take an example that's very important in geology. We have uranium-235 with an atomic number 92, and it can decay into thorium with an atomic number 90 and a weight of 231 plus an alpha particle. And again, this is the equivalent of a helium nucleus with 2 protons and 2 neutrons, so a total atomic weight of 4. So in this case, we are decreasing the atomic number by 2. Those are the protons that are leaving the system. The total number of protons plus neutrons that are leaving the system are 4. This thing is being carried away. And so the atomic weight goes down by 4. So these are the kinds of atomic reactions that occur very commonly when we think about various kinds of geological systems.